So now we have Brian Ferreira from the Federal University of Espírito Santo, a very beautiful state nearby. So if you have the chance to go there, very good, very nice beaches, very nice mountains, and some of the best coffee in Brazil. So without further ado, so we'll hear about symplectic embeddings to systolic inequalities on the sphere.
Yeah. Thank you very much for the introduction, the invitation. So thank you all, the organizers, for organizing such a nice conference with a nice subject. Yes, Espírito Santo is amazing, and we have the best coffee and best muqueca. Okay, so this talk will be about a simple observation that I had in mind a couple of years ago. I was keeping this project for the future, and when I received the invitation, I thought that it would be a good opportunity to get some progress. It turns out that the ideas were full of broken thoughts and then just normal days in mathematics. But today I'm going to talk about what we can get with this simple idea that I'm going to present. First of all, I have this quick review on symplectic manifolds and contact manifolds, but it turns out that seems that I'm a lucky guy today. So Alberto and Johanna already done the job. Thank you very much. So a symplectic manifold is a pair, as we already seen today. So we have an even dimensional manifold and a two form, which is closed and not degenerate. And so this is orientable. And we have the local model due to Darboux theorem. And this generalization, so although not smooth, every smooth manifold meets this two form, as I said, it has to be even dimensional and orientable. And when we go to the cotangent bundle, we have a canonical one, which is exact. So this is the de Rhonde differential of the tautological form, or Liouville, as Alberto called. And this is the main manifold that we are going to talk about today. And we have a lot of other examples as CPN with Fubini study form, surfaces, and products, and so on. And then we can try to study about symplectic embeddings. And we could study like symplectomorphisms, classifying symplectic manifolds, but this is kind of easier problem, but even this easier problem is hard. So a symplectic embedding is just a smooth embedding that preserves the symplectic form. We'll write this symbol, so this right arrow with the S above. And as Johanna recalled, if there exists a symplectic embedding, we have the volume obstruction. And then we already seen Gromov non-squeezing theorem today. So Gromov introduced this theory of pseudo-lobomorphic curves, and this gives non-trivial obstructions for symplectic embeddings, concluding then that symplectic embeddings are different from volume-preserving embeddings. So there's something going on here. And pseudo-lobomorphic curves most of the times gives these non-trivial obstructions. And often we call this situation as symplectic rigidity, because inclusion is the best all you can do. And there are some examples that we have the opposite thing. So we have symplectic embeddings, which are volume filling, as Johanna describes in RP2, or balls in 4 tori. And this opposite thing we call symplectic flexibility, corresponding to volume filling embeddings. Okay, so we have symplectic capacities as well, Johanna defined, but now today I'm not going to focus on normalized ones, just a non-triviality condition that excludes zero function and variance of the volume. So capacities are numerical invariants for symplectic manifolds that behaves nicely with embeddings, scales fine, and are non-trivial in the sense that I just described. So Gromov non-squeezing theorem gives this non-trivial example, the first non-trivial example. I think that these notions were defined by Eklund, Hofer, and Zender. So as Johanna told us, it's hard to construct such a function. And even if it's normalized, it's equivalent to Gromov non-squeezing theorem, which is completely non-trivial. Okay, so we have for the even dimensional case symplectic manifolds, and we have the odd dimensional siblings, which are called contact manifolds. So a contact manifold is a pair of an odd-dimensional manifold and a contact form, as Alberto just defined. We have some examples here. So odd-dimensional Euclidean spaces with the local model, and spheres with the Liouville form, as Alberto just taught us, and also the unit cotangent bundle. So given a Riemannian metric or Finsler metric, if you want, you can restrict to the covectors with norm equals to 1. So this is in particular star-shaped, fiber-wise star-shaped hypersurface in the cotangent bundle. So this is a contact manifold with the restriction of tautological form. And moreover, the Webb vector field, given a contact manifold, Alberto just told us that the kernel of the contact form is a hyperplane distribution. So we have a complementary direction, and we define the Webb vector field to be the unique vector that satisfies is in the complementary direction and is normalized. So this is a global vector field with non-zeros. And for examples, in the odd-dimensional R2n minus 1, this is just the dz component. For the sphere, this is the infinitesimal generator of Hopf vibration. And for unit cotangent bundles, this is dual to the geodesic vector field in the sense of Legendre transform. And in particular, Alberto told us that we have the action of a trajectory, which is just integrating the contact form over the trajectory. And for the case of unit cotangent bundle, let me write like this. So this is with respect to the Finsler metric. The action is exactly the length. Let me write like this. Okay, so this generalizes the study of geodesic flows. And then we have this notion that connects these two notions. So a Liouville domain is a symplectic manifold with boundary and with a smooth vector field, which is transverse to the boundary and points out of the boundary and behaves nicely with the symplectic form. So the symplectic form is exact, and we have this relation. It's not hard to conclude that we have this property, like for Cartan magic formula, and hence the one form restricts to the boundary is a contact form. So as you can see, I'm amazing with drawings and writing. Okay, so for example, we have star-shaped domains, as Alberto told us, and fiber-wise star-shaped domains. I'm going to just draw this fiber-wise because I want to do some observation in the case of S2. So we have this, and a fiber-wise star-shaped domain should be the region enclosed by a fiber-wise star-shaped hypersurface. So on the fibers, we have something like this. So each ray emanating from the zero section on the fiber hits the boundary once and transversally. So it could be convex. So the convex case corresponds to Finsler metrics. And more generally, it could be just star-shaped, as Alberto told us. Okay. So for the star-shaped domains in R2n, the vector field that point out of the boundary is just the radial vector field, and similarly to the cotangent bundle. In particular, these cotangent bundles are Liouville domains because they are convex fiber-wise. Okay, so the main result of this talk is just a simple observation using properties of capacities recently defined by Hutchings and some examples that we can compute. So Hutchings defined maybe 2 years ago a new sequence which somewhat are related to ECH capacities. Another sequence that Hutchings defined This is just defined for 4-dimensional manifolds. Let me write like this. So we have this CK. And also, Hutchins proved that this is always bounded above by this other sequence that I just said. So ECH capacities are bigger than these new ones. And they are symplectic capacities, so they satisfy monotonicity property, conformality property, and non-triviality condition as I defined. And they are even more special. So if W is a 4-dimensional Liouville domain, and suppose that CK is finite, so then CK is a linear combination of actions. So we call this spectrality property. So it relates the numerical invariant for this symplectic manifold, this should be a W here, with the wave dynamics on the boundary. So it's a special property, very interesting. And also, Hutchins called the ball property, which is just the computation for the example of the ball. So the boundary of the ball is the sphere. So this is a contact manifold. This is really a Liouville domain. The ball is star-shaped. Now we put a pi here and call this the ball of capacity A, or the ball of radius square root of A over pi. And we call this the ball of capacity A because the first capacity is given by A. And actually, the sequence is very interesting from the point of view of number theory. So this is given by this. So we start with 0, and then A appears 2 times, then 2A appears 3 times, then 3A appears 4 times, and so on. So this is a nice example, and Hutchins computed using computation of ECH index without the whole powerful machinery of ECH, but you computing ECH index and obtain upper bound via holomorphic curves in CP2. Then we have the second example, for this talk, which is the round metric on the sphere. So D star G0 S2 is the covectors in the Cottonian bundle of S2 with norm lower than or equal to 1 with respect to the round metric. And it turns out that the sequence is also nice. So they are given by linear combinations of 2 pi, and the weight satisfies this property. But in particular, C1 is also 2 pi. And for this, we can compute using, for instance, embeddings, as Johanna told us. So with Vinny, we proved that the interior of the disk cotangent bundle of the puncture sphere is symplectomorphic to the polydisk. The polydisk here is just the product, the symplectic product of 2 disks. The proof goes using integrable systems, as Johanna described. So we consider the kinetic energy and the angular momentum. So this is classically integrable. So the geodesic flow of the round metric is integrable. And then we perturb this with some suitable potential, as probably Yahon is going to tell us better this story, how it goes. And then we obtain, using Arnold-Liouville theorem, action angle coordinates, we obtain some nested toric domains. Let me write like this. And then when we look to the limit case, we can use the symplectic isotopy theorem to obtain the limit symplectomorphism. And the action angle coordinates draw a square. So this is the polydisk. That's the idea of the proof. And then we generalize this to spheres of revolution with Alejandro Vicente. And on the other hand, we have the other symplectic embedding, which is given by the, an explicit symplectomorphism that Oakley-Usher write down nicely in 2016, which gives that the disk cotangent bundle of the round metric is symplectomorphic to the product of the spheres minus the diagonal. Here, sigma is the area form with area, total area 2 pi. And this is very explicit. So this one is maybe magic using limit of symplectic embeddings and Arnold-Liouville theorem, and this is very explicit. But in particular, we have this chain of embeddings. So the polydisk embeds into the disk cotangent bond of the round metric, which embeds into this product. But it turns out that from the monotonicity of capacities that this satisfies this relation, but Hutchins computed in both examples, and they coincide. So the S2 times S2 capacities and the polydisk coincides with the sequence that I just showed in the last slide. So with putting all this together, we get the capacities for the round metric. But in particular, C1 in the round metric is 2 pi. So this is the important thing for what I'm going to talk about. So, okay, so just putting together all these observations and property of the capacities, we obtain such a upper bound on the minimal action. So suppose that we have a 4-dimensional Liouville domain and embedding into the disk cotangent bond of the round metric with some radius. So now I put this R here, meaning that the covectors have a norm lower than or equal to R. Then we need to have this upper bound on the minimal action. And this is just a simple observation, right? Because if the embedding exists, we have monotonicity property, and then by conformality property, we can compute the C1 on the right-hand side. And then by spectrality property, C1 is a linear combination of actions. So minimal action is lower than or equal to this. Okay. So this was the first point of the idea that I had. And then I really believed maybe 1 month ago that it could recover Stepanov estimates on positively curved spheres. But for now, I don't believe anymore. But even so, I think we can do something nice with this. So converse direction. We can ask when the disk cotangent bundle of the round metric embeds into a Liouville domain. And in fact, we can reproduce the argument. But in this case, we just get that 2 pi r is bounded from above by the C1. But it's not true that C1 is always given by the minimal action. And for C, an example that it not holds here, in this context, you can consider Dumble metrics. So Dumble metrics, if you like to go to the gene, you're going to like this metric. So Dumble metrics on the sphere are something like this. We have some Dumble. And this size is not important because for my argument, I'm just showing that C1 can be bigger than the minimal action, right? So consider this metric on the sphere. Definitely it's not positively curved. We have negative curvature here. But we have this stable here, region here. So if we call the radius here epsilon, the minimal action is 2 pi epsilon if we take epsilon small enough, right? So this is the shortest closed geodesic for this metric. But if we take the curvature close to 1 or equal to 1 in this hemisphere here, from our embedding, we have that the ball of 2 pi, capacity 2 pi, really symplectic embeds here in the disk cotangent bundle of this region. Let me call this hemisphere, but I'm not writing this. So we have this embedding here. In particular, C1 of the whole thing should be bigger than C1 of this subset. So C1 is bigger than or equal to 2 pi, and the minimal action is as small as you want. So it's not true that C1 is equal to minimal action for any Liouville domain, and moreover, nor for Riemannian metrics on the sphere. But it could be true for positively curved metrics. We play around with negative curvature here to make this short geodesic, right? Like maybe one could also do something like this, creating a mushroom here. Okay, there are some results that indicates that maybe C1 is equal to the minimal action in sufficiently pinched metrics or spheres of revolution. We can talk about it later. So a corollary of the result is we can consider just the inclusion, right? As I said, if a Liouville domain embeds into the round metric for some radius, we have the systolic upper bound. In particular, you can take as the fibrewise star-shaped hypersurface here is compact, we can take the maximum over all the circle radii. So you just take the biggest one. I think this is bigger than this, right? If it is not, I just cheat a little bit. And then this we call R of sigma. And definitely, we can just take now the round metric with this radius. And then the hypersurface is contained in this round metric. So the inclusion gives upper bound in function of this number. So this is the maximum over all the circle radii compared with the round metric. On the other hand, we can do for the minimal the maximal in radii. So this is the minimal, this is the maximal circle radius of sigma, and we can take the minimal thing. So this circle here. And then the discotangent bundle of the metric with this radius is contained in the hypersurface, in the region enclosed by hypersurface. So we have this other direction, but as I told you, not about the minimal action anymore, just C1. Okay, so this is the first corollary. And playing around with this, we can naturally define a notion for a hypersurface in the cotangent bundle of the sphere. Because we computed C1 for the sphere, and we have these results comparing with the round metric. So I'm going to say that a star shaped in the cotangent bundle of S2 is fiberwise beta balanced if this ratio square is bigger than beta, bigger than or equal. So this is inspired in the pinching condition in the sense of curvature, or even pinching condition in the sense of convex sets in R2N. And definitely, we can use the results above just to obtain an upper bound in function of the volume. And this is not hard. We can just observe that the discotangent bundle of the round metric with radius R sigma is contained in this multiple of the Liouville domain that I'm calling W. And then you use volume obstruction and the upper bound of the minimal action in function of the radius. So we have a way to compare the minimal action with the volume as systolic ratio that Alberto started to discuss here. And definitely, this holds in general, right? So take a fiberwise hypersurface. This is beta balanced for some beta, because this is a compact 3-manifold in the cotangent bundle of S2. So this holds. But of course, this upper bound, it could be terrible, right? Beta could be very close to 0, so this explodes. And so, but this is from the inclusion. Maybe for some special classes, we can produce non-trivial embeddings and recover nice upper bounds. Okay, so of course, this whole discussion could be repeated for any manifold that where you can compute C1, obviously. It's not about S2 or cotangent bundles. So another example is convex domains in R4. C1 of the ball, we computed the whole CK for the balls. So we know the C1 of the ball of capacity A. This is just A. So if you have a convex domain in R4, whenever you have these embeddings, we have these inequalities. And by this remarkable work due to Alberto, Oliver Tmaya, and Jung-Soo Kang, we know that C1 is given by the minimal action as long as the boundary is smooth. And this is strictly convex domain in the sense that Alberto told us is strongly convex. So the sectional curvatures of the boundary are all positive. So this is an amazing result, and I think it's very recent, and it's due to Clark duality, connections of different areas. So it's an amazing paper. I recommend you to read about. And therefore, just comparing the minimal radius and the maximal radius, so the balls are, which are contained and contain X, the convex set, convex body, we obtain this inequality. So with the same idea, we recover Crook-Weinstein bound, which is this one, and Eklund bound, which is this one. And definitely, there are a lot of black box behind it. As I said, spectrality property of the capacities are kind of magical. So I'm not saying that this stuff is easy, but I'm using a powerful machinery to obtain nice results. Okay, so for metrics, as I said, we have Riemannian metrics, we have ellipsoids here, as Alberto told us, and for Finsler metric, convex set. So we can define when a Riemannian metric is beta balanced in the sense of fibers. So this is just that the unit cotangent bundle is beta balanced. So a fiber-wise beta balanced Riemannian metric satisfies this stuff, this inequality. And then from the uniformization theorem, we know that G is isometric to a conformal metric, right? And so we have this magical function here, U, and it's not hard to see. It's straightforward that G is beta balanced if and only if the oscillation of the function U is bounded from above by this value. So this is related to this oscillation. And then now we can use the same results, just restated for Riemannian metrics, and we obtain like systolic inequalities relating the systole and the area, and systole and diameter. So the story starts with Crook, then several refinements, and the best upper bound that we know is due to Rothman. So the systole square is lower than or equal to 32 times area for any Riemannian metric on the sphere. Then we have these sharp results due to Abondandolo, Brahan, Irinevich, and Salomon. And they used symplectic tools, and these are sharp systolic inequalities in the sense that the quality holds just in the Zoll case, so it holds for spheres of revolution and sufficiently pinched metrics. And the thing here is, if you want to prove such result using symplectic embeddings, I think it's very hard because it corresponds to full flexibility of symplectic embedding. So you need to find a volume filling embedding into the round metric, and I don't think so it holds for a general metric. But for some spheres of revolution, I do believe, because of spheres of revolution are related to toric domains, and for toric domains, as Johanna told, we know some nice symplectic embedding stuff. And given a Riemannian metric, Alberto just told us that the volume of the disk cotangent bundle is 2 pi the area, the volume of the ball of the dimension, correct dimension in the area. And then the corollary, when you substitute the volume of the hypersurface in the other result, is that bound. So the systole square is bounded from above by pi over beta times area. Again, this is a good bound if it's sufficiently beta balanced, definitely, but it could be terrible if beta is 0. Okay, and then we can have the same discussion with the diameter, because Calabi-Cole have this remark, a nice remark, using Hirsch inequality and Zhong-Zhang inequality in the first eigenvalue Laplacian. So we can compare the area and the diameter. So we can also compare the systole with the diameter. So the story again starts with Crook, and we have several refinements, and Nabutovsky and Rothman proved the best bound that we know. So the systole is lower than or equal to 4 times diameter for any Riemannian metric. And we also have this improvement when the curvature is non-negative. So the diameter, 3 times diameter, is bigger than or equal to the systole. And in our context, when you just plug and use the inequality that I said, so area is lower than or equal to 8 over pi diameter square, we obtain this nice inequality again if the metric is sufficiently beta balanced. Okay, so pinching versus balancing. You could wonder if there's a relation. It's not, a priori, it's not very clear because it's not positive. I didn't assume that the metric is positive curvature. But it turns out for the ellipsoid metric, beta balanced and pinched condition is somewhat equivalent, but the relation is not linear. So I'm going to rush to end because my time is over. There is a result in preparation that, as I said, beta balanced corresponds to controlling the oscillation. And then we can use some tricks of these PDE inequalities and theorems. Using Sobolev embedding theorem, and we can bound the oscillation of the function u using the Sobolev norm A2. And then we can use the Poincare inequality for the version with zero average and compare, and also integration by parts, and compare this norm with the norm of the Laplacian. And for a conformal metric, the Gauss formula gives control of the Laplacian in function of a pinching condition, for instance. So this is still work in progress. I'm finding this constant, so I didn't finish the estimates. That's why there is a C here. But definitely we can estimate this using, for instance, spherical harmonics and Laplace series, Laplace Fourier series. And then compare when a pinched metric is beta balanced for beta depending on delta. And to this end, I just bring nice problems that naturally arise in the context. So we use the fact of symplectic embeddings giving rise to systole upper bounds, but the results were about the inclusions. So the natural question is when you can do better the inclusion, right? So given a, let's say, pinched by 1/4 metric, which is a natural condition for some properties, do we have nicer embeddings than the inclusion? And the second problem is for which Finsler metrics the C1 corresponds to the minimal action. And there are some related results. We can talk about this later, and I think I'll stop here.